All right, we'll get started. Um, thank you everyone for taking the time to join today. My name is Mark Oliver. I'm a principal engineer here at Varus Engineering, and the topic of today's webinar is adhesive testing and material model calibration for FEA of bonded joints. It's a little bit about me. I've been here at Varus about 11 years, and work with clients on a variety of problems, all kind of centered around mechanical behavior of materials. And one of the areas where I spend a lot of time is working on issues around mechanical design and understanding the mechanics of adhesives and adhesive joints. So just a bit of housekeeping before we get in. So I'll go through the presentation, and then if we've got time at the end, do some Q&A. So if you have a question, you can put it in the chat, and I'll get to as many of those as I can. All right, so the outline for today's presentation, I'll give a brief introduction to Varus Engineering for those of you who are new to us, and then I'll give a little motivation for, I guess, background on FEA bonded joints. Kind of what the key inputs are, and kind of motivate the rest of the presentation. I guess it's kind of an introductory, level presentation. So we're not going to do a deep dive into FEA bonded joints, but just lay some foundation. And like the two main sections will be on adhesive testing and model calibration for cohesive zone modeling. So if you're new to cohesive zone modeling, I'll explain what that is and kind of how we think about approaching calibrating those models and running experiments in the lab to get the data we need to do that. And then I'll say a bit in the fourth section about calibrating continuum material models, kind of highlight some of the challenges that are kind of specific to or adhesives or encountered frequently when modeling adhesive behavior. And then we'll have time for Q&A. So as I said, this is kind of an introductory overview. Hopefully this will be useful to those of you who are doing FEA on adhesive joints, or if you're on the experimental side and running experiments to get data to support simulation engineers on your team. Hoping this will be of interest as well. All right, so just a few slides to introduce Varus Engineering. We are an engineering services firm. Been around since 2006. We're not big. We currently have 12 engineers on staff. Most of us have a PhD in our field of study or an expertise. We're headquartered in Eden, Massachusetts. There's a picture of our building where we most people are based out of here, and this is also where we have our mechanical testing lab. So you'll see some mechanical test data and methods that in this presentation, and that's all done here at our office and lab in just outside of Boston. And as I said, most of us have PhDs. So where we help clients is on problems that require kind of deep expertise in specific areas. And that's primarily in mechanics, either solid mechanics, fluid mechanics, material science, chemical engineering, and electromagnetism. So there's kind of four buckets of daily activity here at Varus. The first is materials engineering. So I have a materials engineering background, as does my colleague Scott Grindy. That's primarily focused on polymeric materials, so polymers, plastics, and adhesives. The second bucket is mechanical testing and material modeling, which we'll talk about quite a bit today as it pertains to adhesive materials. And then we also do a lot of simulation, both on kind of the fluid mechanics and solid mechanics and electromagnetics. And we are a COMSOL certified consultant. So there's a group of us that specializes in multi-physics simulation. And then finally, it's what we call failure analysis. So this can be both for industrial clients to understand if a prototyping is failing, or it can be to support kind of legal matters as well, offering expert opinions there. Okay, so within that context, we do have a practice focused on adhesives and bonded interfaces and interface mechanics. And so our kind of the way we help clients in this area really spans kind of the breadth of the firm, from chemical analysis, which is really kind of geared more towards failure analysis, supporting failure analysis rather than formulation development, doing mechanical testing, material modeling, material model calibration. So this will be kind of the bulk of the talk today, is in these two columns here. We do support, customers with finite element analysis of joints and interfaces, adhesive structures, multi-layer bond structures, et cetera. And then we do have a fluids team. So there are, when things come up, questions around kind of mixing and, flow and processing, which can tie into, the adhesives world. We have experts who have done things and along that vein. So this is this image up here is a static mixer and doing some CFD to optimize the design of those static mixers, which if you've ever worked with a two-parted adhesive, you're probably quite familiar with. All right, so with that, we'll kind of switch to kind of covering FEA or introducing FEA of bonded joints, really kind of motivating the following sections. So I wanted to start by kind of acknowledging that, predicting the mechanical performance of bonded joints or adhesive joints is can be really tricky. And there's a number of reasons for that. The joint strength depends not only on the adhesive, but also, the geometry of the joint, the bond line thickness, the materials that are being bonded, the process history, et cetera. And so, you can't just take the properties of the adhesive and then, automatically extrapolate to how an adhesive joint will perform. So that's one thing. For simulation engineers, one of the common things you'll kind of encounter is that if you look at a data sheet for an adhesive, that you're trying to design with or do some analysis based on, the material, a lot of the data sheets, they don't provide a lot of technical data that you can use as FEA input. And you'll often see things like high strength, outstanding environmental performance, excellent toughness, which as an engineer are not terribly helpful. The third is that data is provided on a few specific joints. So there's the properties of the material, but there's standards that everybody generally relies on for like how to do a lap shear test, and that's done in the standard way so that you can understand what that data means in the context of other adhesives. But that data is often, again, on specific joint geometries and not always directly transferable to more complex or realistic joint geometries. And then the fourth thing that can make predicting joint mechanical behavior really hard is that adhesives are polymers, and polymers in themselves are tricky. Right, so they can exhibit nonlinear behavior. They can be time dependent. It can be heavily rate dependent or temperature dependent in the operating window that they're being used. They have glass transition temperatures, et cetera. So there's a lot of nuances to polymer behavior in general that are applicable to, in many cases, to adhesives. And so one of the best tools that's available to engineers to predict how mechanical adhesive joints will behave mechanically is to use finite element analysis. And the simplest terms, kind of the three inputs, are the geometry of your joint. So this is basically two box beams with a little kind of bracket here. So this is this is an adhesive connecting these two components. There's the boundary conditions, right? So how is this part loaded? What are the loads on the structure? What are the displacements that are being applied, et cetera? And then the third input, which really motivates today's presentation and a lot of the work that we do here at Verist, is the material modeling. So what do you need to tell the finite element program that you're using about how the material or the adhesive behaves? How does it deform? How does it deform over time? How does it fail, et cetera? And there's more than two approaches to modeling adhesive behavior, but the two that we're going to talk about today are cohesive zone modeling and continuum material modeling. So there's these are the two main approaches, and they have very different strengths and weaknesses and limitations. So we'll start with cohesive zone modeling, and I'll describe a bit more in the next section, like what this is. But in short, generally the way that you model the adhesive is just with a single layer of elements between whatever's being bonded together, and you describe how the material behaves in terms of attraction and separation law, which we'll describe in more detail. And these models really excel at predicting adhesive failure. So it's really kind of geared towards understanding how material behaves in an overload scenario, and how damage will initiate and then propagate in an adhesive. So these are very computationally efficient. The limitations are they don't resolve stress through the thickness. You have kind of one element through the thickness, and you do not really capture time-dependent behavior that well. You can add time dependence to these models, but and rate dependence, but in general, if you're interested in something more like creep, or stress relaxation adhesive, then you'd use the second approach, which is a continuum material modeling. So here we're defining constitutive models that describe the adhesive material. These models, it can be difficult to model failure, right? So this is really geared towards kind of strains that are well below the failure point, where the onset of failure may occur. These are more computationally expensive, but you do get kind of a more complete picture of the stress state that's developing within an adhesive, and you can really accurately capture time-dependent deformation. So these are the two main approaches that we'll talk through today. And I wanted to kind of give an example of each, just to provide some more context. So this is an example of cohesive zone modeling. And again, this is really used when you're trying to understand kind of the overload characteristics of an adhesive joint. So how much, how will this joint fail? What are the forces involved in making that happen? What are the energies that involved in making the joint fail? So this is this little toy simulation where we used topology optimization to design a little bracket that's adhesively bonded to a vertical surface, and we're applying a load. So the blue here is where the adhesive is, and so what we used cohesive zone modeling for in this little scenario is to predict the evolution and of damage in the adhesive and the ultimate failure, so that we could predict the force versus displacement response of this little bracket and compare it to kind of a more basic design for the same type of bracket that had the same amount of mass. So we can see that our little optimized material or brackets, stiffer and stronger, and we made those predictions using cohesive zone modeling. So this is a different example. This is more on the continuum side. So another area where FEAs can be very powerful for understanding adhesive behavior is more on kind of the creep stress relaxation realm. So as you get, adhesives are polymers, and polymers are, generally exhibit some viscoelastic behavior. So they will, stress will relax over time, or they will creep. And this can be really important in applications like optics, right? So this is again, a toy problem. We have a metal barrel. There's an adhesive that's bonded, being used to bond a lens to that barrel. And if you define a viscoelastic material model for the adhesive, then you can make predictions about how the warpage in the lens structure may evolve over time. So if you're bonding glass to metal, you have a thermal expansion mismatch. If you increase or decrease the temperature, that will cause thermal stresses to develop in the adhesive, and that can cause the adhesive to creep. And so this is an example where we use continuum models, and we'll discuss this, how we can go about doing this a little bit later. Another thing that you can do, which we're not going to discuss in any more detail, is simulate the propagation of fatigue debonding. So this is just to demonstrate a scenario where if you have a battery pack, so this is an array of battery cells adhesively bonded to a cold plate that's subjected to some external load. And in this particular analysis, what we're interested in is predicting, how a delamination might propagate under fatigue loading in the structure. So we started with an initial debond at the corner, and then you can simulate over time or number of cycles and make predictions about how a delamination would propagate, and how many cycles or how much time it takes for a debond within an adhesive to reach a critical size. Okay, so all right, so we'll that's a kind of introduction of FEA, and get a few toy problems to kind of illustrate where FEA can be used for adhesives. What we're gonna do now is jump into how you go about calibrating cohesive zone models. So the general workflow is as follows. You start with some specimen level testing, and generally you're doing some sort of fracture mechanics test, like a double cantilever beam or an end notch flexure test. And then you're going to take the data from these tests and then calibrate traction separation law, and then kind of you have to square whatever this law looks like with what's available within your finite element code. So you'll generate a material card, and then at the the final step is always, if you want to do some sort of at least verification of the models, you want to simulate the tests that you ran to get the data to make sure that you've kind of input into everything into the finite element code properly. And then validation would be then coming up with another specimen type to kind of measure the load to failure, and then compare that to your prediction. All right. So okay. So first off, what is cohesive zone modeling? This is an approach for modeling adhesive failure, and I mean this can be used to model other materials as well, but it's very powerful for adhesives. So we're going to put a row of elements between two adherents that represent the adhesive. And what we're going to do is we're going to describe the adhesive deformation failure in terms of what's called the traction separation law. So what we're plotting here, and what you put into your finite element code, is a little curve that looks like this, where you have an initial stiffness with a stiffness K, where as you pull the joint apart, the stress in the adhesive will increase linearly up to some point. There's some critical stress or critical separation. Here we're calling it sigma max, at which point you start to put damage into the adhesive, and so then the stiffness starts to decay. And then as you pull the adhesive apart further, you reach some critical separation where you no longer are carrying any stress or any traction within the adhesive. And the area under this curve is the fracture energy. And so these are nice because you capture a lot of mechanics here, right? You're capturing the stiffness of the adhesive, you're capturing a critical strength of the adhesive, you're capturing what's going to be, thought of as the ductility or strain to failure of the adhesive, and then you're also capturing an energy to cause the material to fail. And so these shapes, you can have like a triangular or a trapezoidal or really any arbitrary shape that you want, depending on the code you're using. And so for this kind of trilinear traction separation law, this is what we often plot kind of traction separation like this. But if you are modeling an adhesive being loaded to failure, there'll be there'll be a leading front at the crack tip here, where things are starting to be loaded elastically. And then as you go further back, there's a region of constant stress, and then the stress decays out to some point here, where now beyond here, the crack tip, you're not carrying any stress. So you can think this is the crack tip here, and this is kind of the start of the fracture process zone. So as I said on the previous slide, there's this nice connection between the traction separation law parameters and the many material properties that we engineers are used to thinking about. Elastic modulus, strength, toughness, strain to failure. These traction separation laws are kind of implemented in most finite element codes now to various degrees of sophistication and flexibility. You'll see kind of linear, exponential, trilinear. You can, some codes you can define your own. But what Coase's own modeling kind of boils down to in terms of the material calibration is determining what this traction separation law looks like for any given adhesive. So how do you go about doing that, right? So you've been tasked with modeling an adhesive within some bonded structure, and you need to know what inputs to put into the FEA code you're using. So there's kind of four approaches. There's kind of first one you can estimate from the technical data sheet properties. We'll discuss why that is generally a very difficult thing to do. Second is you can kind of assume you have a bilinear traction separation law and do a series of experiments to calibrate a few parameters. The third, which I'll spend the most time on, is you can directly measure the traction separation laws in the lab. So you can actually run experiments and get what these curves look like experimentally, the full curve, and then go from there. And then the final approach, which we'll discuss, is using inverse calibration. So you kind of rely on this when your adhesive or the specimens you can make are really complicated, and you can't use kind of a nice, cleaner experiment. So, all right. So before we get into those various methods, just a word on specimen prep. If you're going to be designing an experiment to get data to calibrate one of these Coase's own models, it's really critical that you put a lot of thought into how you design your specimens. And you need the kind of the surface prep, the bond line thickness, the curing, the aging of the material. When you make the specimen, all need to really match as best as possible kind of the end use condition of the adhesive. Because the properties that you're going to measure, that you're going to calibrate your model to, are going to be sensitive to all of these things, right? So if you're in your application that you're, or a structure you're designing, your adhesive is being bonded to one substrate, but you go in the lab and you use a different one, you may get results that are not directly applicable. So we run into this a lot where people come to us to get help calibrating a material model, but we say, okay, we can definitely help you, but have you figured out how the material is going to be cured, how the material, what's it going to be bonded to, how you're doing your surface prep? Because if you don't do that first, then you're going to end up having to redo the model calibration in many instances. So you kind of have to get your processing in line and buttoned down as best as possible. And once that's done, then you can kind of go down this route of doing the model calibration. Okay. All right, so the first approach is to kind of estimate from a technical data sheet. This generally doesn't work. This is why. That you have to define a stiffness K in your traction separation law, and okay, so that's generally okay, right? Because most data sheets will have a modulus, and the stiffness is directly related to the elastic modulus and the thickness of the adhesive, and so that's okay. The max stress, the thing on the technical data sheet that you would most likely see would be some sort of tensile or lap shear strength. But in general, the stress that you are going to put into your cohesive zone model is not actually the tensile strength of the adhesive that's measured on the bulk sample, because the stress state is different when you have a bulk sample of the adhesive and when the adhesive is mechanically constrained in the form of a thin bond line. So they're obviously related, but you're not, and it's not wise to just kind of pick the tensile strength off of kind of a bulk specimen and then assume that that's the cohesive strength. If you have nothing else, that's a good estimate, but they're not the same thing. You have to define the toughness, fracture toughness. That's rarely listed on data sheets. And so that, this is where things start to kind of break down. Likewise, the critical separation, you may see a strain to failure, like this adhesive, you can stretch it and uniaxial tension test to 30% strain. So that gives you some sense of the ductility. And again, if you can kind of make an estimated guess about what the critical separation might be there. But in general, this is a difficult thing to do. And the adhesive suppliers know this, right? So one of the things that's happened in the last couple of years is that the adhesive suppliers are starting to provide Coast's own model material cards, for through their websites, or you can reach out to them. So if you have an adhesive that you're tasked with modeling, and definitely check with whoever you're buying the adhesive from. They may have a material card that's calibrated for that particular material. All right, so the second approach is to actually go in the lab and do some experiments. And so kind of the next level of complexity is to kind of just assume you have a bilinear traction separation law. And so if you assume that this is just, bilinear, we kind of ignore any of the complex shapes of this traction separation laws, then we need to input a stiffness, a tensile strength, a shear strength, and then we need to define a fracture toughness for mode 1 and mode 2. And so you can do basically five tests, right? You can do a tension test on the material, you do a butt joint test, and a thick lap shear test to get some measure of the tensile strength and the shear strength. And then you can measure the fracture energy. So for mode 1, you can use a double cantilever beam test, and mode 2, like an in-notch flexure or some other mode 2 test. So this can be this can work really well. You kind of get measurements of the inputs directly that go into the CZM. The problem is that many structural adhesives are not well captured by like a bilinear traction separation law. And so you can kind of introduce some significant errors, which I'll have a case to convince you of that, if you assume the traction separation law is bilinear, when in fact it's not. All right, so the third approach, which is really our go-to whenever possible, is to directly measure the traction separation law. And you can do that using standard fracture mechanics test specimens. And so the traction separation law, sigma, the function of delta, is defined as the derivative of the J integral with respect to the crack tip separation. And so if we take the double cantilever beam test, which if you've done any adhesive testing, this is probably, you're quite familiar with this. If you run a double cantilever beam test, you can calculate what the value of J is at every point in time in the test, because J is just a function of the applied load that you get off the load cell and the beam opening angle theta. So I don't have it marked here, but that's the angle that's formed between the two beams as you pull them apart. So you can measure J at every point in time, and the crack tip separation, delta, you can actually measure locally, right? So there's different ways to do that. The way that we do this in our lab is to use digital image correlation. So we'll put two cameras on this test specimen. So you can see one is kind of focused on the free ends of the test specimen, and we use digital image correlation to measure this beam opening angle theta. And then we put a second camera on the crack tip and measure locally what the crack tip separation is. And so this works really well, particularly when you have like structural adhesives that are at least 100 microns thick and exhibit some significant ductility. Obviously, as adhesives become much thinner, or the failure strain becomes much smaller, then you run into limitations about the separation that you can measure with digital image correlation. So you can do the same thing with an end-notch flexure test. The J integral J is a function of the load P, and then 3 angles, theta A, B, and C. So we put boxes at the 3 load points and measure the beam rotations. And then we put a second camera and measure the local crack tip displacements. All right, so what does this look like? What's an example of this data, right? So you go in the lab, and what we do is you run this test, and the data that you get out is the J integral. J is a function of the crack tip separation. And so this is experimental data that we extracted from a double cantilever beam test. And then the traction separation law, so that basically what you have to tell Abacus or Ellenstein or whatever finite element code you're using is just a derivative of that curve. And so the gray line here is this taking the numerical derivative of the black curve, which is the J delta curve. And so there you have it. So that, from a double cantilever beam test, which, are ubiquitous, if you measure things in a slightly different way, then you can get out, from that test what the traction separation law looks like. So in this particular case, there's like an initial region here. There's a peak stress of around 8 megapascals. And then you can see that the stress decays as the separation increases. And this one had a critical separation of around 1.2 millimeters. So this is kind of a more ductile, softer adhesive. And then once you have that traction separation law, you then have to kind of fit whatever your finite element code, can actually describe in the program, right? So, there's a trilinear function is very common, and so if you fit a trilinear function to this data, you get a nice fit. And so, from a double cantilever beam test, we've measured the J delta curve. You differentiate that, you get your traction separation law. You then can fit that to whatever your finite element code is using, and then there's your inputs, right? So that's what you put directly into the FEA code. So you can do this, the example I showed was for mode 1, but you can do this for mode 2 and under mixed mode conditions as well. And so that's how you can go about, calibrating traction separation laws. Then the final step, as we touched on a little bit earlier, is to kind of verify that you've defined your material card properly. And kind of the first step is always to simulate the test from which you got the data to calibrate the material card. And so if you do everything properly, then you should see that the FEA and the experiment agree well when you plot the force versus the load line displacement. And if you see any significant discrepancies, then that tells you need to kind of revisit how you're doing the model definition. All right, so the fourth approach that we'll use is a little less clean, but sometimes you don't have any choice. And this is basically called inverse calibration. So this is a case where we had a glass device, and there was an adhesive that was used to bond a thin polymer sheet to it. And we needed to calibrate a cohesive zone model for the debonding of this sheet from the glass substrate. And the kind of best way to get samples was to kind of have these glass discs bonded to the plastic sheet. And so it was difficult to make, what you call like a standard test specimen. And so what we did in this particular case is we kind of used a vacuum chuck to kind of hold the glass in place, and then designed a little fixture to basically, peel this off. And so this is kind of a peel test in which kind of the peel arm length and the angle are constantly changing. So it's from a material property point of view, this is a terrible test. But if you're kind of doing a finite element analysis of your test anyway, then all these complexities are okay because you're going to be simulated anyway. So the fact that your bond length, the width of your bond varies as you move around this circle, and the angle of loading changes, doesn't really matter. And so one thing you can do is you can then kind of run a series of experiments, or sorry, series of simulations, kind of map out different combinations of peak stress and fracture toughness, and generate a series of force displacement curves, and then compare that to what you measured experimentally, and kind of make an educated assessment about what would be some reasonable cohesive zone model retraction separation law parameters to input to describe this debonding process. And so these inverse calibration tests, this really kind of come in again when the geometry of the specimens you can make are a limiting factor. One other thing I want to touch on, because cohesive zone modeling is used a lot in simulating impact conditions. So certainly in automotive, right? I mean, in automotive world, cohesive elements are used all the time in crash simulations because adhesives are such an important part of the automotive structures now. And so you can measure, you can define rate-dependent cohesive zone models or traction separation laws, which can be really important in these kind of crash or impact models, because the adhesives, again, they're polymers, so they will exhibit some rate dependence, and the strength and the toughness that they exhibit will depend on how quickly you load them. And so in that case, what you have to do is actually subject the adhesive to loading rates or strain rates that are representative of the application. And so there's a couple methods we've used here to get at those properties. So we have kind of what we call like an impact wedge test. So the duration of this video is a few milliseconds, 15 milliseconds. So you drive a wedge into the adhesive at a couple meters a second, and then using high-speed video, you can get the beam deflections, and then we can get a measure of the fracture toughness at these high rates. And this can be, again, really important for these crash applications. We've also done, we have a drop tower here where we've can do basically these fracture mechanics tests at impact rates. And so we drop a sled, which impacts the specimen at several meters a second. And again, using high-speed video, we can do an end-notch flexure test. And from this, you can get out the fracture properties at impact rates. Okay, so we've talked about several different approaches for calibrating cohesive zone models, right? From the very simple of kind of guessing based on the technical data sheet to directly measuring the traction separation law. I wanted to, this is a little example that kind of maybe motivates why it's important to think about the shape of the traction separation law and not only rely on these bilinear models. So this is a comparison. So these two traction separation laws, the one on the left, we're calling the actual behavior. So this is this was calibrated by going in the lab, running the DCB and an end-notch flexure test to measure what the traction separation law looks like, and then fitting a trilinear model to that. The one on the right is the bilinear approximation for the same material. So if you look down in this table, these two material models have the same stiffness and tension and shear, the same ultimate tensile strength, the same shear strength, and the same toughness in mode 1 and mode 2. But clearly they're not the same, right? And so the shape will affect how stress develops and distributes within the joint as you load a specimen. And so what we're showing here is just a standard lap shear joint model where we've used this bilinear approximation to what we're calling the actual CZM. And in this particular case, if you were to simulate these, the strength of a joint, this difference in CZM shape results in a pretty significant difference in what you would make, the prediction you would make in terms of how much energy is involved in causing this joint to fail. So if you use the bilinear model, we're predicting that you get, beyond, well beyond, the strength that's required, or the force that's required to yield the substrate. And so you get up to these higher loads where you're now dissipating energy by plastically deforming the substrates. And you end up with predicting an energy to failure that's, nearly double what we predict with the actual CZM. So it's so the shape of your cozy zone model can definitely matter, and so it's something to keep in mind as you're selecting these models. All right, so we'll change gears a little bit and talk about adhesive testing, material model calibration for kind of the continuum material modeling approach. So again, we're getting away from modeling failure. Right? So cozy zone modeling is great for modeling failure. And now we're going to turn towards, modeling kind of rate-dependent or time-dependent properties of materials. So think again back to this kind of this lens warpage problem, where understanding the creep in the adhesive and how that affects the warpage on the structure is important. So then that's where we rely on these continuum material models. So that is the same sort of process. We're going to start with specimen level testing, but unlike in the cozy zone model calibration, where we're usually using like fracture mechanics based tests, here we're using generally kind of bulk tests. So we're treating the adhesive generally as or the polymer, so you can cast or cut out specimens of the tensile specimens of the adhesive, or you can test the material using the kind of standard compression test. Then once you with that raw stress strain data, then you can calibrate constitutive models that can capture whatever it is that you're trying to describe, the yield strength, the rate dependence, change in stiffness, etc. Calibrated material card. And then this is obviously not an adhesive, but this, for any sort of like polymer material calibration, again, you want to do some sort of validation test where you do a direct comparison of some experiment to the FEA of that experiment and do a comparison of what you can measure. So this is a force versus compression curve for a 3D printed lattice. And again, while this is not an adhesive, the same methodology applies. All right. So what I want to do in this section is be a little shorter is just kind of touch on some of the common challenges with testing adhesives, getting like kind of the quote bulk properties of adhesives, and some of the approaches that we take here at Veris to get at some of these. So the first challenge, is specimens can be very thin. So I'm thinking of, many adhesives will come in like a film form, right? And so it comes off a roll. You can like cut out a specimen. Sometimes they cure, sometimes they don't. Right? If you have like an optically clear adhesive that can just come as a freestanding film. So there can be challenges in particularly getting compressive properties of adhesives in these thin form factors. So I'll touch on that. Soft adhesives are highly rate dependent. So the cozy zone modeling, usually we're doing that for structural adhesives. Think automotive adhesives that are generally highly cross-linked. They may have some rate sensitivity. But if you're working in the world of adhesives that are used more for like energy absorption, right? So soft PSA, foamed PSAs, etc. Those materials can be very rate dependent, and getting the high rate properties can be a challenge. The third and fourth ones I'll touch on kind of together because those are use the same kind of same approach. Getting high frequency data, right? So again, if you're worried about if you're using an adhesive and you want it to like for kind of damping vibrations, for example. You need to know how the material behaves at very high frequencies that are difficult to test at. And then finally is long-term creep. So I just wanted to have one slide on each of these four things and give kind of examples of things that you can do that are non-standard. So the first thing is, testing of thin films. So if you have adhesives that come in thin films, the one thing that can be really challenging is getting kind of compressive properties of the film without having to layer up a whole bunch of layers to get some thickness. So this is a kind of a custom test fixture that we created specifically for measuring compression of thin polymer films. We've used this a lot for adhesives as well. And this sits inside of a universal load frame, but you put 3 samples of the film that you're interested in. And we've done this for films down to at least 50 microns, I think maybe lower. And then you can put a top platen on, you can apply a compression through the thickness. And the challenge with these experiments is getting a good measure of strain, right? And so what we have is a displacement sensor that sits in the middle of these 3. And so this can measure the displacement of the top platen with, sub-micron accuracy. And so we've used this, to get at the problem of through thickness compression of very thin films. And, you could do this both to get, just monotonic stress strain, but also look at things like creep. So if you are, if you do have these very thin films, you may have to come up with new methods that aren't standard. The other thing is the high rate dependence of soft adhesives. Many of these like really soft adhesives, the stiffness can change, many times over like an order of magnitude of strain rate. And so, particularly if you're interested in scenarios where an adhesive is involved in an impact event, right? Imagine, consumer electronics, you have some sort of adhesive, somebody drops their thing, it hits the ground. The strain rates that the adhesive can see can be very high, right, into the thousands. And so if the strain rates you care about are in the thousands of strain per second, and the material is very rate sensitive, then there's no way to kind of run a quasi-static test and extrapolate it out. So you actually have to get the data at the strain rates that are relevant to the application. And so this is the pneumatically driven impact test frame that we've developed specifically for soft adhesives. So you can, measure the adhesive stress strain behavior in shear. This is an example of data on the soft adhesive that was at 1500 strain per second. We can also run this in compression and get up into the thousands of strain per second. So this is like a soft adhesive, and you can see how as you go from 80 to 700 to 1700 strain per second, the material becomes much stiffer and stronger. And so again, for a lot of these high rate testing, there aren't good standards. You've got to kind of get creative in how you do the experiments. All right, so the last 2 things I want to touch on is one method that we use a lot here for adhesives of various kinds is called DMA, or dynamic mechanical analysis, time temperature superposition. And so this first example is to basically predict the long-term creep behavior of an epoxy. So this was a 2-part epoxy, and we wanted to know, like, what are the creep characteristics at room temperature up to, beyond a year. And so you could go into lab, you could set up a creep test and monitor it for a year, which we've done. But, that's in many applications, that's not a practical timescale to run an experiment. And so instead, what you do is use time temperature superposition. So you can do this in a DMA. So you make a specimen of your 2-part epoxy, and you can measure the creep strain as a function of time at different temperatures. And you run these experiments, over kind of minutes, minutes to hours, something that's, reasonable for an experiment to run. And then what you're doing is we're using time temperature superposition. Now what that does is basically treats running a test at high temperature as 50 C is the equivalent to running that same experiment at a lower temperature, but for much longer times. And so you take these three curves that were collected at different temperatures, and then you create a basically calculate some shift factors, and you create this. What you end up with is this universal curve. So this is the creep strain versus time, and then what you can get out, you can make predictions about how the creep will evolve. In this particular case, after 2 years. And so, again, for applications where thinking optics and other similar things where an adhesive may be subjected to a static stress, and any kind of creep in that material could affect the shape or deformation of adjacent layers. This is a powerful tool. And the final one methodology is using DMA time temperature superposition, but instead of going long times, you go to high frequencies. And so if you have an adhesive that is going to be in a structure, and one of the things you want that adhesive to do is say absorb vibrations in the megahertz range, then or you need to understand how it reacts in the megahertz range. It's very difficult to measure how stiff and lossy material is at 1 megahertz. So what you do again is test the material. You do a frequency sweep. I'm sorry. So we test the material over kind of a range of frequencies that is experimentally easily accessible, like 1 to 10 hertz. And then you do that at a series of temperatures. And then you shift those curves. So testing at colder temperatures is equivalent to testing at higher frequencies. And you generate, again, a master curve. And so this tells you, you get a model that gives you the tensile, the storage, and loss modulus as a function of frequency, out to frequencies that are way beyond what you can directly measure experimentally. And so once you have that data, then, again, depending on the FE code that you're using, you can define this in different ways. This is an example of an Abacus input file. So the blue dots are the experimentally measured curves, and the black lines are the fit to get out to these high frequency, higher frequencies. So it predicts, how the adhesive will behave in some application. So, all right. So with that, thank you for taking the time to tune in. Hopefully, this was informative and people will learn some things. So I've got a few minutes I can stay on and answer a few questions. Okay, so I see some questions coming in the chat here. Okay. All right, so the question about for cohesive zone models, do you use node merge between the cohesive elements, or do you use tied contact? Yeah, so generally, I mean, yeah, generally I will use, if you're using cohesive elements in Abacus, like a tie constraint is adequate. And matching, if you can match the mesh great. If not, that's generally not a problem. You need to use what are the understand the mesh requirements? Special mesh requirements. Okay. Yeah, so we didn't get into the numerics, but the question here about kind of meshing of cohesive elements. I mean, this is a big topic, but kind of some general thoughts. I mean, cohesive zone modeling works best when you have, your fracture process zone, is basically engaging, like at least 3 or 4 elements. And, just like, in general FEA terms, right, you want to find enough mesh to kind of resolve the gradients and stress, for example, that develop in a part. The same thing is true for an adhesive, right? So if you have an adhesive and the fracture process zone, is 2 millimeters, but your element size is 10 millimeters, then that's going to cause a problem. So now that said, in a kind of automotive world, if you're doing a full body crash simulation, you have no choice but to use big elements. And so what we'll do in that case is we will do like a mesh sensitivity study. And kind of the way that we like to go about this is you measure the traction separation law, you kind of define a cohesive zone model that is, mesh, that works for small mesh or fine mesh. And then you run kind of the same, you simulate those tests with the mesh that will actually be used in the final analysis. And often what you see is as you go to finer, or coarser meshes, you'll start to lose energy, And so you'll have to do like a mesh compensated model definition. And so if you are having to use large elements, then what you want to do is basically simulate some sort of like DCB or in-notch flux or test at different mesh densities, and then figure out how you need to compensate the fracture energy to make up for the numerical errors that arise out of using a very coarse mesh. So that I think that's what I would say on that. You get a copy of the recording afterwards. Yes, I'll send that out. All right, here's a question about DMA TTS applicability. Yeah, so if you're doing DMA TTS, right, you're making some assumptions that you have like a, rheologically simple material. Depends on how critical the accuracy is of your creep data. So an approach that we will often take is to run a DMA test, use TTS, and then get a creep curve. And you do that first because that's something you can get quickly, right? And if it's important to kind of have at least some data to go on and analyzing the creep in the structure, then that gets you started, right? And then when you do that, you also kick off a series of creep tests, that run over, weeks or months. And as that data comes in, you can compare it back to your TTS. And if you can kind of verify that, oh yeah, the creep curve that we collected with TTS is, conservative, and the creep isn't actually is going to be as high as what we've been predicting. And so there's a bit of there's always some uncertainty around using TTS, and so it's really kind of what sort of verification you need and how much really depends on your application and the importance of the accuracy of that creep data. And what we've done, what I described of doing the TTS and running creep tests, we ran a creep test for 3 years, and we kind of verified for 3 years, as the more data came in, that the TTS curve that we calibrated was adequately or I guess sufficiently accurate for that application. There's one. I got time for one more question about discrepancies, slide 30 and 29. Actually, I can't see my second. I'm able to see my slide numbers there for a second. All right, so I see discrepancy results in slide 30, whereas in the former slide 29, even though traction sequences are again different. Yeah, so for I'm completely following, but 29 and slide 29 on the impact testing, that was a different material than it was on slide 30. So that those aren't directly comparable. All right, some techniques to use to estimate failure of adhesives and continuum models. Yeah, short answer is yes. I mean, it depends. You can always use like a critical strain failure criterion, but or critical stress, right? So it is possible to use continuum elements, do element deletion. I think what the best numerical or what's the material modeling approach is, and the experiments you want to run to kind of calibrate that is very specific. But like short answer, yeah, you can definitely add failure and damage to continuum elements for adhesives. I haven't done that a lot, generally because the cohesive zone modeling approach is so good and efficient generally, and for most applications for modeling failure. All right, so I think I'm out of time, so I'm going to end the meeting. If people have other questions, please reach out. I'd be happy to answer those over email. So m oliver at veris.com. I'd like to thank everyone for tuning in.